Hi. So in the previous video, we discussed the fundamental theorem of line integrals. And now I want to discuss path independence. So we're going to say the integral of f over the path c is path independent if provided c is going to connect 2 points, say p and q. So here c actually refers to all paths that connect points P and Q, where P and Q are specified. We're going to say that it's path independent if for any path from P to Q, you have this equality, right? So the only thing I changed was how I got there, C1 and C2. So to make the point, right, so say that this is C1 and this is C2. In the previous video, I showed that, in general, those do not have to be equal, right? But if they are, we say that the integral is path independent if they're always equal. Okay, so previously I referred to a loop. So officially, what I called a loop is actually called a closed path. So a closed path is one where the starting point and the end point are the same thing. And what I want to show you is that an integral is path independent if and only if, that means that the implication goes both ways. So if this is true, the result follows. If the thing I'm about to write is true, then it's also, the left-hand side is true. It's also path independent. So this is true if and only if the integral of f over c dr is equal to 0 for every closed path C. Okay, so the emphasis here is closed path. Okay, so let me explain why this is the case. So this is path independence on a domain D. So there's some region of space, maybe not all of space, but some particular region. So it's path independent on the domain D if, so the function f, right, the function f is independent of its path, provided this always obtains for every closed C inside D. So this should not be too difficult to see why it's true. Let's take a closed loop and let's add a single point, and we'll say this is P and this is Q. So I'm going to go this way and this is C1, and when I go this way, we'll say this is C2. Okay, so far so good. So if I integrate from C1 and then integrate through C2, this is a closed path starting at P, and P is in this domain D. Okay, well, part of the hypothesis is that any path, all paths that are, if it is path independent on D, then I'm claiming every closed integral is going to be 0. Every closed path is 0. So to see this, all we have to do is turn this around. So flip the direction of this, and we're going to call, that's actually going to be called negative C2. That's a new path where you flip everything. Now if this does not feel familiar, if that feels like a trick, think back to when you have negative, say 1 to 0 on your integral. What do? You flip it, and then you lose the minus sign, right? That's all we're doing here. We're just flipping. And if you check your definition, this will make sense. You'll see that when you flip the order, negative sign is going to pop up. Okay, so what about C1 and negative C2? What can you say about them? Well, they have the same starting point and they have the same end point. And because they have the same starting end point and we have path independence, it must be that they are equal. But if they're equal, then when I flip it back, right, then I'm negating the whole integral by that fact up here. But if I'm negating it, that means it's the opposite of that. So when I glue the whole thing together, right, just like if I had a 0 to 1 plus 1 to 2, we could just say that's the integral from 0 to 2. Same thing here. So I'm gluing the whole thing. So now it just becomes the integral c rather than c1 and c2. It's just the whole thing. Well, because c2, negative c2 is equal to c1, it follows that c2, if I said that wrong, but I think you get the point. When I do the whole thing, they're going to cancel. And so when I take the whole path, it's equal to 0. Okay? Now, conversely, if every loop is equal to 0, I can pick any point on that loop, place a point, chop it into two parts, right? Flip one of them, and because they have to cancel, then they're going to be opposite in sign. So what did I say just now? All I did was repeat the argument that this has to be 0, but I assumed now it's going to equal to 0, and I showed that it's going to also have to be path independent. So the logic works both ways. So in summary, here's the point. Path independence means that if you have 2 points, right, you fix these 2 points, and in some region of space called the domain, right? So if I ask about all the families of integrals that I can take, I claim that that is path independent only if the integral from here to here does not depend on path. And all I've done now is prove that if it does not depend on path, then any closed path integrals are going to equal 0, meaning those integrals where these points are the same, or when I go a full circle. So if I can go a full circle and it's always equal to 0, then it'll always be path independent, meaning that between any 2 points, the path does not matter. Conversely, if between any 2 points the path does not matter, then all closed integrals, meaning all integrals that start in at the same point, they're going to equal 0. Okay, now here's a very nice result. Suppose I have a conservative vector field, right? If I have a conservative vector field, then it's going to be path independent. So this is on page 1128. So let's remember, what is a conservative vector field? Well, a conservative vector field is an f that is equal to the gradient of another function, right? So we say that capital F is equal to its potential function, the derivative of its potential function. So this is a conservative vector field. Now, what I'm saying right now is that every conservative vector field is path independent. Okay, so why is this true? Well, let's say that we have this f over c dr. I'm just going to replace it with this gradient f. So I get this right here, right? This is just what it means to be conservative. Nothing special here, okay? Now, by the fundamental theorem of line integrals, I can split this up as f r b f r a. So how does this show that a conservative vector field is path independent? Well, let's look at it. Here I have this curve C. Now, suppose I give you a different curve that also has the same starting and end points, right? So we're trying to show that this will always give us. We're trying to show that this is going to be independent of path. So in order for that to be shown, we have to consider two integrals that share the same starting point and ending point. Otherwise, there's something to be shown, right? So let's consider two paths that start at RA and RB. Remember, A and B are like time, and RA is a point P and RB is a point Q. So you have these 2 points. Well, I'm doing this integral, right? So this could be, say, C1. So this is C1. Well, by the fundamental theorem of line integrals, I just pick up those RAs and RBs, right? I sort of forget about the path, right? But wouldn't it also be true that this is equal to C2, right? So I think you get the point. I can say that this is equal to C1, and this is also going to equal this, right? Also by the fundamental theorem of calculus, but I've picked a different curve. And then finally, since this is the potential function for our conservative vector field, I can now replace this with C2 and I get capital F. So on the far left of the equation, I have the integral right here over C1, and down here I have it over C2. So it's the same integral, same value, but the path is different. So this proves that it's path independent. In the next video, we'll do computations. See you.